Hello, it's Keith here, and this is lesson 8 of the YQuest series, and in this lesson we're going to be looking at the platform-specific code of the MSX1 version, which you can see here, and as usual I'm playing it quite badly. Anyway, it's not my gameplay that's on test today, we're going to be looking at the code. Let's go over to it now and let's have a look. Okay, here's the code for the MSX1 version of the game. So we're going to go through all of the code here. The code is loosely based on the simple series, the joystick reading routine, which was based on the bitmap routine. So if you've not seen those, I'd suggest have a look at them. We're going to skip over the code that's been used previously fairly quickly. I'm assuming you have an understanding of those kind of basics. So if you don't, please have a look at those. Anyway, let's make a start on the platform-specific MSX1 code. So first of all here, we've got some collision masks. Now, on the MSX1 version, we're using the tile map to draw the graphics. The tile map is limited to an 8x8 grid, but the actual resolution internally of the calculations is much higher resolution, and this causes a problem because it might look like your object isn't overlapping the enemy, but the collision detection routines might think you are and might be wanting to kill you. So to avoid that, we're actually masking out the bits that aren't being represented properly visually of the internal logic, and this means the collision detection will work at the same resolution as the visual display, meaning that won't happen. So this is used by the multi-platform code for that purpose. We're then defining the offset of the user RAM. This is for the parameters of the game. Or the same parameters are defined on every system, but the memory location is different on each system. Next, what we're doing, we're defining the screen size. This is for the common code there. And then after that, we're defining the addresses of the VDP ports for the MSX1. We've then got some common definitions here. These are used by my multi-platform tutorials. These basically allow me to assemble on different systems, things like that. So those are fairly common. And then what we've got here is the cartridge header for an MSX1 cartridge. After that, we're then turning on our screen here. We're then transferring the bitmap data, the pixels, the black and white pixels if you will, to the pattern data within the video chip, and then we're defining the colors for the same tiles. Now the tiles include 96 font characters and also the 4 banks of sprites for our gameplay. Of course, these are all actually pattern data used by the tile map. I'm using the term sprite in a rather loose term for today's lesson. We're then clearing the user RAM here. Now we're going to start drawing the title screen. We reset the number of lives, 0 the level number, and just start up the player object just here, and then we're just silencing the sound. We then clear the screen and we start drawing our title picture just here. Now the title picture is in the data definitions. We've seen those in a previous lesson, and what we're doing here is we're adding 96 to the tile number and showing to the screen. Why 96? Well, the first 96 patterns are the font and the rest are the actual bitmap sprites. So we're having to add 96 to jump over that font. We're then showing the fire message, the URL from my website, and also the high score at various locations on screen. And then we are having the start level code. The first thing we do, we wait for the fire button to be pressed. This also happens when a new level starts, you see. We then clear the screen, put the player back in the center of the screen, and we initialize the level data which defines what objects are in this game level, so enemies, mines, things like that. We've then got our main loop. Here we're just waiting and reading in from the joystick. If any joystick keys are pressed, we're going to have to process those later. We store that in D for now. And then once we've done that, we get ready to start drawing our player to the screen. First of all, we clear the old position of the player and we draw the UI to the screen. The UI is the high score, the number of lives, things like that. They all appear behind the other sprites. Next, what we're doing here is we're checking the key timeout. Now, if you hold down left or right, you will increase the acceleration of the player sprite. But we don't want to do that too fast, otherwise the player will quickly get out of control. So if the player holds right, then we only process that pressing of the right button every so often. And so if the key timeout is not 0, we're going to skip over the holding of that button. Next, we're processing the keys. Our key presses are in D at the moment. We loaded it in here. We're using this read joystick routine we'll see later. And what we're doing here is we are just changing the acceleration according to which directions are being held. The acceleration will alter the player's movement. When it comes to the fire buttons, we're having to do a separate call. We're using operating system calls for convenience here. So read joystick is just reading up, down, left and right. Unfortunately, it doesn't read in fire. So we're reading in fire here. We need to select the fire button here with A. A1 is fire 1 on the joystick. A3 is fire 2 on the joystick. If the player presses fire 1, we're going to fire a bullet. If the player presses fire 2, we stop the acceleration, just stopping the player dead all of a sudden, kind of like a handbrake stop there. So that's quite handy if you need to, if you're losing control of your player maybe. But if the player's pressed a direction key, we're setting E to 5 in all cases, not with the fire buttons, and that is setting the key timeout, and that will ignore any more presses of those direction buttons. Once we've done that, we're just looping all the way back to the top here. That's our main program loop. You can see there's not a lot of it. The vast majority of the code is being done by this draw and move, and that's multi-platform code, and that's the key. We want to get as much as possible in that multi-platform code, and that means that porting this game to a new system is usually 30 to 60 minutes of work. It's hopefully very fast. That's the idea anyway. Now, the rest of the code is really relating to sprite routines, generally speaking. We've got a print character routine here. The font is actually more sprites, more patterns rather, so it's just the same as every other piece of data, the same color depth and everything. So what we're doing here is we're subtracting 32. Our font has nothing below a space, you see, space is character 32. And we're then loading in X and Y from the cursor position. Cursor X is immediately after cursor Y, so loading BC from cursor Y will load in cursor X as well. And then we're just jumping over here and we're directly showing a sprite to the screen here. If we are loading in from an object, then we're having to do things slightly differently. We're getting the sprite frame. The sprite frame selects which of the 4 banks it uses. Each bank contains 16 sprites, and so to do this, we're loading in the sprite frame and then multiplying by 16, and we're loading that into H here, and then adding the sprite number of the object plus 96, because the first 96 patterns are the font, remember, and then we're adding the calculated bank offset here, and so when we get to this point, the H register will contain the sprite number of the object loaded in from IX plus the bank offset plus the 96 that are used by the font. We're then loading in the X and Y position from IX again, the X and Y position of the object, calling the VDP screen position to select the X and Y position of the object we want to draw, and then transferring the tile number to the VDP data port, which will set the tile on the screen, and that effectively draws the tile pattern on the screen that we're using as a sprite in this example. Blanking sprite, basically the same here. We're just using tile 0, which is the space character of our font, and that will clear the current sprite. Clear the screen. Well, we're just doing a very crude effect here. We're just looping around every single object on the screen and setting them all to 0 here. Not very advanced, but it'll work. It'll do it in an emergency. Get VDP screen pos, set write address. We've covered these before in the simple series, the bitmap example. The get VDP screen pos will take a BC X and Y location, and it will set the VDP to write to that address. So a quick way of setting any particular tile of the tile map. And set write address is selecting a memory address in HL as the next write position in VRAM. So those two have been used before many times, and that's what's doing the graphical work for us. Finally here, we've got some stuff here where you can see we've got our font here, and then we've got the 4 banks of sprite data for the 4 banks of animation here. We're using ZX Spectrum graphics here because they're 1 bit per pixel. It's basically the same thing. A slight lie here when I say the color definitions of ZX Spectrum, they're not, they're MSX exclusive, but the Spectrum doesn't have them. Actually, I'm not porting YQuest to the classic Spectrum. I'm doing the Spectrum next, but the classic Spectrum, I'm not such a fan of it. I think it looks like a nice game in 16 colors, but it would be a bit hard to do in the Spectrum colors a decent job of. So as I say, a bit of a lie here when I'm using the term Spectrum here. I'm just referring to it as 1 bit per pixel really. So we've got our black and white information here, and then we've got our color information here, which need to be loaded to 2 separate addresses, and that was done in the header. Now here's finally our read joystick routine. What this does is it's using the firmware call 00D5, and we have to pass an accumulator. 0 will select keyboard, 1 will select joystick 1, and 2 will select joystick 2. So we're using joystick 1 here, although I was controlling it with the keyboard, but that was a function of my emulator. So that's what that does. Here's our wait for fire routine. This will wait for fire to be pressed and released. That's so we can do a bit of a debounce. So if the player's mid-gameplay holding down the fire and then they get shown the level complete message, they have to at least release fires before they continue to the next level, otherwise it's a bit confusing. So that's what we're doing here. And all the time we're waiting for fire to be pressed and released, we are re-randomizing the random seed. When we undo random, the random seed changes. So that's just a simple re-randomization. Now we've got here a bunch of includes for the common data, the common code, which is the multi-platform code we've looked in the past. And we've got a do out IR here, which transfers large amounts of data to the VDP. It's basically the equivalent of an out IR command, but it allows us to use a 16-bit counter here. Finally, we've got here the initialization routine for the screen, and then we've got an org to C000, and that just pads out our cartridge to 32K because OpenMSX doesn't like cartridges that aren't a multiple of 16, which is perfectly understandable, really. And that's really all there is to it, and that gives us our complete game. As I say, there's lots of other code. If this is the first lesson you've seen, of course, there's going to be lots missing. You're going to wonder where it is. It's all multi-platform, so please see episodes 1 to 5 of this series, which are the multi-platform code, and they will explain what actually is doing all the rest of the work of the logic of the bullets and the collision detection and the movement of the enemies and things. As I say, this is just the platform-specific code for the MSX1. The game's free, it's open source, and you're totally welcome to download it, modify it, and do whatever you want with it after that. Release it as your own work, sell it if you somehow manage to do that. I totally encourage you. It's entirely up to you. I don't need any credit for it or anything like that. So if it's any use to you, if you want, then go ahead and download it and make what you can of it. I hope you enjoy it. I hope you've enjoyed this lesson. If you have, please like and subscribe. Liking videos helps YouTube rank them and recommend them to other people. And I've got a forum and a Discord if you want to chat. So please give that kind of thing a go if that's what you like doing as well. But whatever you do, I hope you have fun with your programming. I wish you a lot of success with whatever programming or artwork projects you do. Thanks for watching today, and goodbye.